Okay, so as I was saying, on Friday we learned how to approximate volume under a surface using rectangular prisms. Today we're going to learn how to find volume using integrals. There's one more little learning target that I forgot to stick on this front page, where we're going to learn how to find average value of a surface. So average z value of a function. If we get to it. If we don't get to it, we'll push that to tomorrow. So here we go. All right, in chapter 14, notice I have like my Thanksgiving slides out. So in chapter 14, we studied, this is happy turkey. We studied partial derivatives, which involve differentiating with respect to one variable while holding all the other variables constant. Chapter 15, we're going to do the same thing backwards, right? So suppose, if you remember the warm-up on Friday, we found the partial derivative f sub x equals 2xy. This means we held y constant while differentiating with respect to x. So if we wanted to undo this, we would hold y constant again and integrate with respect to x. So technically, now I never rewrite with my constant variable out front, but you could put the variable that's being held constant, you could move that out in front of the integral, because technically it's being treated as a constant, and you're really just integrating what's left. So the antiderivative of 2x is x squared. The y comes along as a coefficient, right? And then you have plus some unknown constant, which of course could be a function in terms of y, right? Because if you had an f sub x, all the terms that had y's but no x's would go to 0, right? So anyway. All right, that's kind of a little review. So here's what I want you to try. I want you to try first just anti-differentiate. Don't worry about doing the definite part. Let's first just make sure we've got our antiderivatives the same. Let's just do this. And then we'll do a spot check, and then we'll plug in our limits. So for this, what variable are you holding constant? X, right? Okay, so the x is being held constant. So you do the antiderivative of 2y to the negative second, which is negative 2y to the negative first. Raise the power by 1, divide by the power, right? It's been a while. Okay, so you'd have negative 2 x squared y to the negative first. All right, and then for your other term, the antiderivative of 2y would just be y squared, and then you would normally have a plus c, but and then you'd have to plug in the x and the 1. So I'm just going to write it here. So we have, let's see, so we have negative 2 x squared y to the negative first plus y squared evaluated from 1 to x. So what are you plugging the 1 and the x into? Y, because you integrated with respect to y, so those are y values. So go ahead and plug in the x and then subtract plugging in the 1 and see what you end up with. Oh, you know what it is? So when you are integrating, plug in. That's it. This is supposed to be a all right. Okay, any questions on this? All right, taking it up a notch. Now, this is called an iterated integral. It's also called a double integral. So an iterated integral, when you evaluate, and we'll talk about this in a little bit, but I'm going to warm you up. Do you want to try this without me teaching you anything?
No.
Yes. Think inside out. That's all I'm going to say. Think inside out. Give it a shot. Okay, so the first integral that we want to do is the with respect to y, which I have here. Okay. So the first, I did too much in one step. I'm going to do it step by step. Okay. So you have the integral from 1 to 2 of. All right, so if we integrate with respect to y, so we end up with negative 2x squared y to the negative first plus y squared evaluated from 1 to x. Oh gosh, that looks familiar. And then there's still this dx sitting out here, right? So this whole thing, what is this equal? We already found it up here. I didn't even notice that. Okay. So you end up with 3x squared minus 2x minus 1 dx. Now you anti-differentiate with respect to x, and you get x cubed minus x squared minus x from 1 to 2. Plug in the 2, you get 8 minus 4 minus 2, which is 2, minus 1 minus 1 minus 1, which you get plus 1. So you end up with 3. How do we do? Not bad. Okay. All right. So the double integral you just solved is called an iterated integral. You work these from the inside out. The limits of the inside integral normally contain functions. This is going to drive me crazy. That are in terms of the outer variable. The limits of the outer variable have to be constants. And I will show you visually why and what this means. But for the final solution to be numeric, those final limits have to be constants. Okay, so the limits identify the boundaries of a region. So just like last year when you did an integral from 3 to 7 with respect to x, this bounded the region from x equals 3 to x equals 7. Now with 2 variables, you get 2 boundaries. So here's what ends up happening. I'm going to draw some more things. So the inner boundaries, these are y values, and then these are x values. So what does this mean? This describes, like this right here. So this is the function y equals x plus 5. This is the function y equals 2x squared. So this is our region, except we got to know where to start and where to stop. I just kind of assumed that it was at the 2 and the 5, or the left and right points of intersection, but it's not. It's from here, wherever that is. I don't know what this point is. Let's just say it's here, 2 to 5. So what ends up happening is this bounds your y values, the functions that bound your y's, and then this says take these boundaries from this starting x value to this ending x value. And that's your, this is not what we're finding the area of. This is our region R. And so this right here, whatever that is, makes your region R. This is your z value. These are heights. I'm going to tie this together in just a minute. So what are you doing? You're adding together all of your heights of your surface bounded by this region. So basically, you're taking all the ordered pairs bounded with these boundaries, plugging them into your z function and adding them all together, and you end up getting an exact volume. Okay, we'll get to that. All right, so what is a double integral? All right, if f is defined on a closed bounded region R in the xy plane, then the double integral of f over R is the limit as change approaches 0. I love it's just a delta symbol, but that's notation we'll talk about in a minute. So as change approaches 0, really it means change in y and change in, it's the all of, as we like surround the point. So as the space surrounding the point approaches 0, have the sum as I goes from 1 to n of our z values for every possible area value. It's kind of weird. So area is like the area around a point. As that area approaches 0, you end up with just the point times, which is like your area. I'm having a hard time speaking today. When you have a rectangular prism, it'd be like the area of the rectangle, and then your z is times the height, and you let that area of the rectangle approach 0, and you end up just getting a point times height. So anyway, this is not something you have to know, but it is the actual mathematical formula behind the integration formula. So here's what really happens. So the value of the double integral is equal to the volume of the region between the surface and the xy plane bounded by R. We will get into ones between surfaces. Those we'll do with triple integrals. So you could always, of course, subtract the z's and do it with a double integral, but it's more fun to do it with triples. So most of our triples are just going to be surface xy plane. All right, so using old methods, if we were to find the volume of this lovely shape right here, so it has triangular region R, and it's got this plane that's kind of slanty. And if we're trying to find the volume of this shape, well, you can't do it by rotation, so you have to do it by cross-section, right? So what would we used to do? We would do, as x goes from 0 to 2, and we would add the areas of all the cross-sections together, right? So we'd have to come up with a function so that we'd have 1/2 base times height, area of the triangle, and then add them all together from 0 to 2, and we get the volume of the region. Now, what we can do instead is find the z function for this plane, and then you do as y goes from 0 to whatever this line is, and as x goes from 0 to 2, and then you just plug in your z, and you do a double integral. So anyway, so what they're showing you here is you're going out first to the y, and then the x tells you how far out to go this way. So the y tells you where to stop this way, the x tells you where to go this way, and then the z is just what you're plugging in to know how high at every single point. Anyway, so volume with a double integral would be the volume. This is kind of this little notation here, this double integral with an r on the bottom is like a shorthand to say double integral over the region R. The region R is usually made up of x limits and y limits, and then there's your function right there. So for this problem, if you the integral as x goes from 0 to 2, the integral as y goes from 0 to 1/2 2 minus x of your plane equation. Okay, let's do some problems. Yes. There you go. Okay, so your book in 15.1 only does double integrals with numeric limits. It doesn't introduce limits that have variables in them until 15.2, but we're going to go ahead and this is only numeric limits too, but we're going to do both today just because it's fun. Plus, I have to teach you something else today that you didn't learn last year. So we will actually do it. All right, but let's see how we do with this. So we're going to evaluate, this is going to find, let's think about this. Our region R, X goes from 0 to 1, Y goes from 0 to 1. What shape is region R going to be? It's a square, right? It's a little square, 0, 0, 1, 0, 1, 1, 0, 1, right? It's a little square, and then the height is all determined by this Z function right here. So take a minute and you can set up, by the way, for these, it doesn't matter since everything's numeric. You can go dx dy or dy dx. Makes no difference. You'll get the same answer either way. How many of you want to go dx dy? Raise your hand if you've already started. Have you gone dx dy? Okay. How many of you are going dy dx? Okay. Those of you who haven't started yet, do a dx dy. All right, so I did mine dy dx, and I was just talking with this group. Most often, you're going to do dy dx, just because most of the time, if you have, now with numbers, it actually makes no difference at all. But most of the time, your region R, if we're just talking in the xy plane, you have some function and then some other function, right? These functions are usually solved for y in terms of x. So like if this is, I don't know, make up some function. Let's pretend this is x cubed plus 3. And let's say this is y equals x minus 2 squared, and pretend that that's touches. Okay. All right. So anyway, so you got some set of functions. And then whatever your x values are for wherever you want to start and stop, whether or not they intersect there. So the functions, since they're already solved for y, that's your f function, right? Whatever your z is. And then your outer would be like, say this is x equals 0 to x equals 3, right? dx. So your function like top minus bottom, if you remember last time when we did area, so we would do top function, top boundary, bottom boundary from here to here, right? So top minus bottom, here, here. So now you're not really doing top minus bottom, you're literally just writing top boundary, bottom boundary from x equals goes from here to here. Now, once in a while last year, do you guys remember we'd have to turn it sideways? We'd have some, and then we'd have to solve the function for x. So when you have that, if it's already like x equals something, then of course you'd want to do dx dy because your functions are defined in terms of y, so they're solved for x. So if it's already solved for x, then you'd want to do dx dy. But if it's solved for y, you're going to want to do dy dx. But it's these four things, bam, 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 bam. Those are what outline the area of the region that you are integrating over in the xy plane. And then your z, is just how high do you go. So anyway, that being said, so we integrate with respect to y, we get this, and then you integrate that, plug in the 1 minus plug in the 0, and then you're left with that, and you integrate that with respect to x, and when you're all done, you get 2/3. If you did it vice versa, you'd get the exact same thing. Any questions on this? Yes.
So how can you flip it when it's constant but not when it's variables?
So for this, the constants were both 0 to 1, 0 to 1. If it was x goes from 0 to 1, y goes from 0 to 3, you would flip the order and you want to make sure you have the right numbers with the right variables, right? You can flip if you have functions too. It's just not as easy because if I have like that last example, right? So if I have some function solved for y and some function solved for y, and then say my x like goes 0 to 3. So this is y equals x squared and x plus 5, whatever. Of some f function dy dx. you need to create the same area, but now if you switch them, your y's would have to be constants and your x's would have to define your function. So watch out, because in order to create this area using x's, you would have to actually like split it up, right? Because you need a right x and you need a left x, and you need a right x and you need a left, like, do you remember when we had to do right minus left? If you had to do this right minus left where you were creating functions for your x, it's not an easy switch. Now, these functions I didn't actually do. Someday I'll actually do an example out of my head where I draw the picture that I'm actually talking about. So here, x squared, x plus 5. Okay, so there's the actual thing. So if I wanted to switch this so that it was x equals, so then if this is the function y equals x squared, you get x equals plus or minus root y, and you get x equals y minus 5, right? So this would be x equals root y. This would be x equals negative root y. We're getting really deep into this stuff, like way deeper than I was planning on going today. So you would have to do an integral as y goes from here to here, with this on top, this on the bottom. And then as y goes from here to here, with this on top and this on the bottom. So you'd have to do x going here to here with these y values, and then x going here to here with these y values. It's not just a cute little switch. It's a big process. Yeah, which we will do, but not today. Okay, but now you know why. Like, if they're just numbers, it's easy, but if they're functions, it's a whole new world, right? So, okay. Okay, I might skip this and come back to it. I have to teach you a concept today called trig substitution, which we skipped last year. Do you remember us skipping that? Because of all the snow days. Tejesh, you should have learned trig sub 2 years ago.
Yeah, we did that. Yeah.
Yes, we did. Last year we had like 45 snow days, and so we had to cut trig sub. So I have to teach you trig sub, but before, you have to leave at 1:45, right? Before you go, let me at least give you the we're going to skip this. Let me give you the formula for average value, just so that you know it. It's not that bad.
That was for me. Like, I personally felt it was pretty difficult.
All right, average value, you just take the volume of your region and divide it by the area of your boundary, the area of the region R. So it's volume divided by area, and what you end up with when you take the whole volume divided by the area of the enclosed region, you're left with your average Z value. Okay, so take a second and let's see if you can do this. So find the average value of f of xy equals xy if your region R is a rectangle with these 4 vertices. So let's see if you can start it start to finish. So finding A takes 2 seconds. That's just the area of a rectangle. But I want to see if you can set up the definite or the double integral with your correct x limits and your correct y limits. Again, since they're all numeric, it doesn't matter which order you go in. All right, so let's talk about this. So first, if you're me, you'll draw a picture, right? So we have vertices at 0, 0, 4, 0, 4, 2, 0, 2. So if you draw a little picture, so this is 4, 2, then you'll know, well, first of all, what's the area of the rectangle? 8, right? It's 4 by 2, 8. So the area of the rectangle is 8. Our x's are going to go from what to what? 0 to 4. Our y's are going to go from 0 to 2, right? So it doesn't matter which order you go in. I went dy dx, makes no difference. So 1/8 integral 0 to 4, 0 to 2, xy dy dx. Did my dy first and got 1/2 xy squared plug in your 2 in, remember, you're plugging it in for y, so you get, that's 4, so you get 2x minus 0, so you end up with the integral of 1/8 times 2x dx, and now you integrate with respect to x, and you get x squared, evaluated from 0 to 4, so you get 16/8 or 2 minus 0, and your average value is 2, which is the average z value. When you're doing average value in 3 dimensions, it's the average z value. The average height, basically, of your surface above the xy plane. All right. I have one more average value, which is like, okay, without evaluating, we're just going to set it up. It's actually not as hard as you'd think. Like if you read, it's a lot of words, but doesn't make it harder. So a firm's weekly profit in marketing 2 soft drinks is P equals that function, where X and Y represent the number of units of the 2 soft drinks. Write a double integral that it would equal the average weekly profit, right? So P is your weekly profit. So we want to find the average weekly profit if X varies between 40 and 50 and Y varies between 45 and 60. So go ahead and take a minute and just set it up. You don't have to evaluate. Just do the setup. Since all of your limits are numeric, again, it doesn't matter if you go dx dy or dy dx. So you just have an integral where your x goes from 40 to 50 and your y goes from 45 to 60, but you need to multiply it out front by 1 over the area of that, whatever that rectangle is. So it would be a 10 by 15, so 1 over 150, right? And then times your integral, so of your beautiful function. So I went dy dx. Most of the time we're going to be doing dy dx. Any questions on that one? All right, we're not going to use calculators yet to do these. Instead, we're going to go back to this guy. No, because I got to teach you trig substitution. All right, so this problem appears to be deceptively innocent. However, it requires trig substitution, which you did not learn last year. So you might need it for some problems this year, so we're going to walk through this together slowly, step by step. Find the volume of the solid bounded by the paraboloid z equals 4 minus x squared minus 2y squared in the xy plane. Notice they did not give us any limits. We got to find our own. Yes, no. So the first thing that we're going to do is find limits. I kind of want to open the slide and just delete everything, and we'll just walk through it together. And if this goes south, I don't know. I do have it typed so nicely. All right, we'll try it and we'll see how it goes. Okay. So the first thing that you have to do is find your limits. So what happens is the first thing we're doing is we're finding where this surface intersects the xy plane. And you're going to come across this a lot over the next month. Where does this surface intersect the xy plane? Well, what do you know is true anywhere on the xy plane? Z equals 0, right? So if z equals 0, you set your z equal to 0 and solve. Once you solve, you get x squared plus 2y squared equals 4, right? Something like that. So now we have to figure out limits based on this function. So this is going to be like our total boundary. So if you solve this for y, you get this. You get y equals plus or minus the square root of 4 minus x squared over 2, or 2 minus 1/2 x squared. All right, this, by the way, what shape is this thing? It's not a circle, it's an ellipse, right? So, and let's see, so you'd have a 4 over the x over 2, so it's wider this way. So pretend that's my lovely ellipse. All right. So we have some ellipse. So if we solve this for y, we get y equals your top boundary and your bottom boundary. But you need to give it starting and ending x values, right? So now we got to figure out where is here and where is here. Well, sometimes it's just obvious and sometimes you need to use a little bit of thinking. In this case, since the ellipse is centered about the origin, if the x values would be wherever y is 0, they'd be on the x-axis. So you now set your y equal to 0, you get x squared equals 4, so x is plus or minus 2, and there's your x limits. So you have to kind of figure out that and figure out that by setting your y equal to 0. So first you set your z equal to 0, solve the thing for y, then you set your y equal to 0, solve it for x. It's not always set y equal to 0. Sometimes you have some shape that's like over here, and then you have to do other work to figure out your starting and ending x values. It's only because they happen to be where it intersects the x-axis that you set your y equal to 0. All right, so let's set up our integral. So we're going to do a dy dx. So your x limits will be on the outside, -2 to 2. Then your y limits, negative root 2 minus 1 half x squared, positive root 2 minus 1 half x squared of your z function dy dx. Now, first lesson of the day to help your life be a little bit easier. Take a look at what I have right here and tell me why I was allowed to do that and why that would still give me the same thing. Yes, exactly. Because of the symmetry, you can go ahead and just find it in one quadrant and multiply. You've got to be careful though. In this case, we're okay. The x's and the y's are all symmetric. You got to make sure. Sometimes you can be fooled because just because your r is symmetric doesn't mean your z is. So even though your r might be some real cute little shape that's symmetric about the origin, if your z is different, has different values here than it does here, you can't just take this volume and times it by 4. You've got to take all the different z's into account. So you've got to make sure not only is your x symmetric, your y symmetric, but your z also has to be symmetric. So in this case, it's a paraboloid. It's going to be the same in every quadrant. But you got to just keep that in mind when you do the little shortcut. So anyway, so instead of going -2 to 2, I went 0 to 2. And instead of going negative root to root, I went 0 to root. Okay, so go ahead and integrate dy. Everyone can do this. This is a piece of cake. Yes?
So on the outside, why is it 4 on the outside?
Okay, so because we were supposed to go -2 to 2, so instead, like say we kept this. So say this guy right here was negative to positive, right? And all I did was change this lower x to 0. Then what I'd be doing is I'd just be doing 0 to 2, right? So if I just wanted my x's to go from 0 to 2, just do this guy, then I would double it, right? But instead, I not only did my x's, but I also did the y's. So on our picture, what I'm really doing is just doing this guy right here. So then I got to do it times 4. So that's where the 4 comes from. It's from me trying to make my life easier, because it's a lot easier to plug in a 0 than it is to plug in -2 minus 1 half x squared under a square root. All right, so once you anti-differentiate this, which means you just get this, that's the answer right there. The hard part now is you got to plug this in for all your y's. The zeros just go to 0, but you got to plug this guy in for all your y's. Do you have a question? All right, so you have this beautiful function. So you got? Yeah. Okay. So now, once we've got this, so what I think, let me see how I cleaned it up. So I factored this guy out of these two terms and put the 4 minus x squared here and factored this root out of each of these. And then here, just cancel the 2's and have this times this guy, which then, oh, that's kind of nice. So you have a 4 minus x squared to the 3 halves in both terms. So you pull a 4 minus x squared to the 3 halves, like out of both terms. And what are you left with? You're left with 1 minus 1/3 root 2, or 1 over 3 root 2. So anyway, or 1 over root 2 minus 1 over 3 root 2, which is 2 over 3 root 2. There you go. The 4 just stays out front. Took a little fun simplifying. When we get into problems where we hit something like this, try to look a lot for GCFs. Anything that you can just keep pulling out and pulling out and pulling out. Usually what ends up happening is you'll end up with something that's kind of not so bad. Yeah. Yes. So, I'm going to do it on board. All right, so we have 4 minus x squared times square root of 4 minus x squared over 2 minus 1/3 4 minus x squared square root of 4 minus x squared over 2, right? I'm just rewriting what's there without the integral stuff. Okay, so the first thing I'm going to do is I'm going to pull this 1 over root 2 in front. And then this stuff that's left, that's 4 minus x squared to the 1/2. You with me? All I did was take this little guy and moved him in front. Okay? I'm going to do the same thing with this little guy. So I get 1 over 3 root 2 times 4 minus x squared times 4 minus x squared to the 1/2. All right? I have a GCF. I have the same thing in common to both terms, right? Really, these are just like terms. This is just numeric coefficients. I don't even have to put it. I can just combine like terms. So 1 over root 2 minus 1 over 3 root 2. Well, this is like the same thing as if I find an LCD. 3 over 3 root 2 minus 1 over 3 root 2 equals 2 over 3 root 2 times this thing. Well, this thing is the same stuff inside. So it's just 4 minus x squared to the first times 4 minus x squared to the 1/2. You add your exponents and you get that. Oh, nothing, right? We haven't even started on the drink stuff yet. Okay. All right, is everyone together? Yes? Are you there?
I'm there.
You're there. All right.
I don't get here.
Now, I don't know what I've got next, but I'm thinking I'm going to move this whole big coefficient and put it all in front. Because remember, numbers can go in front of the integral. So I might have put in an 8 over 3 root 2 up front. Let's see. Oh, and I've rationalized. So 8 over 3 root 2 times root 2 over root 2 gives you 4 root 2 over 3. All right, so that's all I could do as far as cleaning it up. Now we got to anti-differentiate this thing. trig substitution works great when you need to integrate quadratic functions raised to powers. I know that's kind of an unusual set of functions, but it comes up from time to time. So when you need to integrate quadratic functions raised to powers, that's where you're going to use your trig substitution. Okay. So, I don't know if I have anything else here. No, I don't. Okay. So here's how you do trig substitution. And I probably have a picture. I do. I'm just going to redraw it so that I don't give too much away too early. All right. All right. This we don't care about. It's just a coefficient. This is what we're looking at right here. This 4 minus x squared to the 3 halves. So we want to label the sides of the triangle. So let's see. This is going to be 2. I could put the x here or here. I'm going to put the x here. And then this is going to be this. So you look at each of the little terms of your quadratic. If you have something that's a trinomial, you have to complete the square to get it a binomial. So anyway, so you look at the terms of your quadratic, and if there's a minus, then this guy has to be the hypotenuse, and this has to be one of the sides, so the Pythagorean theorem works. If it's a plus, then these would be the 2 sides. So you label the sides of a triangle so that one of them ends up being whatever this guy is. Don't worry about like the exponents yet. You just want one of those sides to be 4 minus x squared when you do your Pythagoras. That, again, don't worry about the exponents. Just worry about getting one of those sides to look like that. Okay. All right. So does everyone understand how I picked the sides for the triangle? This is trig sub first time. Okay. All right. Once you pick your sides, you start labeling trig functions. So what ends up happening is, let's see, I need something that will give me this. So I could say if I want this over this, that would be sine. This is like we'll call this theta. So I could say sine theta equals root 4 minus x squared over 2. So now I could say, hey, that means root 4 minus x squared equals 2 sine theta. All right, you got to do a second function. Pick an easy one. So the easiest other function that I could see to pick would be cosine. So because then your cosine theta would be x over 2. So x equals 2 cosine theta. Because cosine theta is x over 2. Now, how do we use the second function? We're going to use this to find our d theta and our dx so that we can do some substitution. All right. So what we're going to do is we're going to replace this, all of this, with trig. So the first thing we're going to replace is this guy. So the 4 minus x squared to the 3 halves, well, if it was like, say it wasn't to the 3, like we already have the 1/2 part, but say we didn't, say we just had a 4 minus x squared, that's okay. You can have sine cubed or sine to the 3 halves or whatever, right? You can have sine with exponents, that's okay, right? In this case, you have 2 sine theta is this guy, and it includes the 1/2, because that's that to the 1/2, right? So this part would actually be equal, if we cube it, would be equal to 8 sine cubed theta. Is that okay? Does that make sense? Okay. All right. Then, so you got that part. Then you got to find the dx. So now you use your other function to find the dx. Dx equals -2 sine theta d theta. It's kind of like a u sub, but instead of substituting with u, you're substituting with trig. We haven't even done a U sub yet this year. Would have been good if we started with a U sub before we jumped into trigonometric substitution, right? So I wanted a triangle where one of the sides, let me erase some of this stuff. I wanted a triangle where one of the sides ended up being that. Okay? So how do I get that? Well, think of it as this something squared minus something squared. Think Pythagoras, right? So this is 2 squared, this is x squared. Since I'm subtracting, this needs to be my hypotenuse. No, you're not an idiot. Believe me, you're not an idiot. Okay? So this needs to be my hypotenuse. So this is going to be one of the other sides. I tend to like to put the easier side on the bottom, but it doesn't really matter. So anyway, that means that this squared plus this squared equals this squared, or this squared equals this squared minus this squared. Does that make sense? So that's how we did the chart. Oh, good. See, I got some more O's. All right. See, it was good you asked the question. Okay. All right. So now what we're going to do is rewrite our integral in terms of trig. Okay. So sine, there's me just cubing both sides. So you get that. And that's me showing you how you get the d theta and the dx. So now we are going to replace. We're going to replace this guy with 8 sine cubed theta, and we're going to replace this guy with negative 2 sine theta d theta. And we get, oh, I don't need to see too much. Let me reveal this way. And we get this guy right here. Oh, no, we don't. We get this guy right here. There we go. Oh, by the way, if you change your functions, now you got to change your limits, right? So in our original function, these were x values. X went from 0 to 2. Go to where you relate x to theta. If x is 0, then divide by 2. You get 0 equals cosine theta, so theta would be pi halves. If x is 2, you get cosine theta equals 1, so theta would be 0. So you're going from pi halves to 0. But the nice thing is that since this is negative, you can flip them and make it positive. There's a lot of good review in this problem. We're like reviewing half of integrals in a day. Yes?
So like, what if instead of 4 minus x squared being your like base function that you did everything around, if it's like 4 minus 2x minus x squared?
You would have to complete the square to get it into binary. Yeah. I don't think I've ever asked one that tough. Not in Prop 3. I've asked one that tough in AP. You guys really lucked out that we dropped trig sub last year. So, all right. Okay, so anyway, so then all I did was flip the limits and make it positive. So you flip the limits and you have 64 root 2 over 3 sine to the 4th. Now, sine to the 4th. So this we didn't skip. This was section 8.2 or 8.3 last year. Trig functions raised to powers. So when you have sine to the 4th, when you have an even power, so what do we do? So if it was an odd power, you just pull out a sine, convert the rest to cosine. But it's not. It's an even power. So you got to think of it as sine squared times sine squared. Convert one of the sine squareds to cosines, right? Which is 1 minus cosine squared. So we're going to start off by, let's see, there's that. Okay. So we're going to start off by thinking of this as sine squared times sine squared, converting one of the sine squareds to a 1 minus cosine squared. Easy peasy, right, Jack?
Yeah.
Yeah. All right. Yeah, we're not done yet. Yeah. You're not done.
Welcome to the club, man.
Okay. All right. So now we want to distribute. Oh, wait. No, I just went ahead and jumped in and did my power reduction. Okay. So, I did a power reduction on both of them right away. I don't know if I would want to do that or distribute first. I don't know. I did a power reduction on both of them. All right. Well, I'll just do it. Okay, we'll do a power. We're going to follow what I have. So we're going to do a power reduction. All right. So, all right. Okay. So do you guys remember when you had to anti-differentiate cosine squared or sine squared? You had to do power reduce. Reduce. That doesn't sound familiar? No? I even talked about Looney Tunes when I taught it. Okay. So anyway, so sine squared is equal to 1/2 times 1 minus cosine 2 theta. And cosine squared is equal to 1/2 times 1 plus cosine 2 theta. These are your power reduction identities, and they turn squareds into single powers. That was a thing. We did not skip it. I guarantee you did it last year.
Oh, that? Okay, I remember this.
You remember power reduction?
No, I remember like the 1/2 and like the 2 theta.
That's power reduction.
Yeah. That's what it is?
Yeah. Because you're taking a higher power and reducing it to a lower power.
So, we're solving that for the.
So I went ahead and I did both. So I replaced my sine squared with a 1/2 times 1 minus cosine 2 theta. And I replaced my cosine squared with a 1/2 times 1 plus cosine 2 theta. It's kind of fun. Right?
Yeah, did you
All right. So let's see here. I distributed this 1/2 in, so I got 1 minus a half, which is a half, minus another 1/2 cosine 2 theta. So that's this guy right here. This guy just came along, and this guy went ahead and moved out here and made the 64 become a 32. So I just did a little cleaning up. So I distributed the 1/2 and combined like terms, and then this became this. And then this guy, I multiplied by that so that I could get that. You never knew integrals could be this big, huh?
Wait, are they doing trick sum and AP Calc this year then?
Yeah, absolutely. They're absolutely doing trig sub and AP Calculus this year. The only reason we dropped it last year was because of snow. We normally spend 2 days on it, and that gave us 2 days back.
Give them my condolences.
So, now, to be fair, it's not my call, because I'm not teaching any BC this year. So, yeah. It's all Miss Greenwald. It's her decision. All right, so once you have this, I pulled out another 1/2. So these little 1/2s, I factored those guys out times the 32, and then the 32 became a 16. Why do we what? I didn't hear your question. Okay. And then I multiplied these two guys together, 1 minus cosine 2 theta times 1 minus cosine 2 theta, so, and got that. So This essentially is your 1 minus cosine 2 theta squared. We're almost done. We still have to power reduce this guy.
What?
Because you're back to another square, right?
Back to square one.
So you got to power reduce this guy. So every time you power reduce, right? So cosine squared theta is equal to 1/2 times 1 plus cosine 2 theta. But here it's cosine squared 2 theta. So you got to double it. So you end up with 1/2 times 1 plus cosine 4 theta. Every time you use a power reduction, you're doubling your angle. It's a lot of good. This is like the review of all of last year in one problem. Okay.
Oh, I knew that.
All right. Then from here to here, that's just me cleaning it up and combining like terms. I just did 1 plus 1/2 and got 3/2. It's the only difference between there and there. All right. And now we are ready to anti-differentiate. So we're in d theta mode. So the antiderivative of 3/2 d theta is 3/2 theta. The antiderivative of -2 cosine 2 theta. So I don't know if you guys remember this. Essentially, when you first learned it, you did a u substitution on it, but then later on we learned that if your input is linear, you can just divide by the slope. So the antiderivative of cosine is sine. So this would be -2 sine 2 theta divided by 2. You divide by the slope. Remember, if your input is linear, you just divide by the slope. Right? So that's how you get that guy. And then your last one, again, antiderivative cosine is sine, divide by the slope, and you get 1/8 sine 4 theta. All right, we have anti-differentiated. We're ready to plug in the constants. So you plug in a pi halves for theta, minus plug in a 0 for theta.
Look at everything 0. 0, 0, 0, 0.
That would really annoy me if at the end the answer was 0. And it couldn't be 0 because you know you have stuff above the xy plane. Just so you know, the same concept for z integrals for volume goes as for like x and y integrals, where if you have some z above and some z below, the z below the xy plane will be negative and the z above will be positive. So if you're truly finding volume, you need to do just your positive z's and then absolute value of your negative z's and add them together. We don't really get into that very much. I don't know if I ask you any questions where you have to do that. All right, that is trig substitution. Normally, this problem is given to students who already know trig substitution. So you just got, introduced to it by fire. Are there problems on your test? I will answer that question as we get further into the unit. Okay? I'm tabling that question until we are farther in just to see how it goes. Okay.